that might be a second piece of the recording today. Okay, so where am I trying to go? Okay, so we just finished chi-squares. Okay. So next is ANOVA, right? Analysis of variance. And as the name would suggest, we're trying to understand the source of the variability in our data. So there's variance, there's variability, there's noise, right? And we want to understand what variables are explaining some of that beyond just error. Okay, so we could just have, that just happens to be the case, it's a noisy variable, but there might be meaningful predictors, right? There might be individual differences that predict the differences in scores, etc. So, for example, with our earlier little groups here, is the difference between the groups, we want to know, is it attributable to the effect, quote unquote, of the pill, or is it just error? Is there anything else? Okay. So in other words, we're looking at whether the difference between the groups that we've attributed to the pills, is it bigger than the variability between the groups? So is blue versus green bigger, more meaningful difference than the difference between this kissy face guy and his own group? Okay, because that's the variability, that's noise. So what we're trying to do is we're trying to look, there's the total variance, and we're going to try to proportion it, okay, into the variance that is due to the group, that's treatment versus no treatment, and the variance that's due to error, that's kissy face versus blue group. And we're going to create a ratio of this so that if the variance that's explained by our effect, our treatment effect, is bigger than the variance that is explained by error or not explained by the model, this is it will be a significant effect of treatment. Okay, so if the hypothesis is null, that means that the top of this bar here is only error compared to error. There's no effective treatment. The alternative hypothesis that there is a difference between the groups is that there is an effect that is due to this pill, the treatment, that is greater than the error, and then even when we divide by the error, that is still left in our ratio. This will be null, basically, and this will have a positive value for treatment. So then if we do this ratio, we take the ratio of the variance that's explained by the difference between groups, and we divide it by the variance that's explained by error, essentially, and that we're looking at the probability of that ratio of that size being larger than you would expect based on just error. Then we would say we're accepting the alternative hypothesis, that there's a treatment effect, and rejecting the null, that there's no treatment effect, that there's no difference between groups. Yes?
Sorry to go backwards, but everything's building from group one. First off, we're looking at relationships between variables.
Yep.
What are we going to put in our equation? Secondly, depending on, we wouldn't say there's a correlation. And then what we did just a moment ago as well, looking at, is there group differences?
Yep.
And if so, then we run this, just reinforces.
Yeah, and you don't have to start from the beginning. You could say you don't have to do a t-test, right? Your question could be, a t-test and ANOVA in some cases will be very similar, right? If you're looking at, is there a difference between groups as another way of doing a t-test. But this additional, an ANOVA framework will allow us to put more than one variable in. So the t-test is just considering, is there a difference between group? Group is our one variable here, treatment, right? Or whatever the group variable is. Like we had control versus epilepsy, that group variable. But in an ANOVA, we're going to build on this, and we're going to see we can add more than one factor to try to explain as much variance as we can, as much as a piece of pie of variance as we can. Does it make sense?
Yeah.
Okay. So another way of describing this is we're looking at the same thing we were doing earlier, looking at group differences, but we're asking again, is the group difference between the two groups bigger than the variability between groups? If so, how much of that? What variables can we attribute it to? So currently, I'm not really moving past the t-test right now. This is just another way of looking at our t-test. But we're going to add different variables to it now. Is everyone with me so far?
If you did your t-test and didn't find a difference, would you move on to this stuff?
If you were just looking at the same thing, right? You just had the group variable, the way we did it before, controls versus epilepsy is our group variable, and we found a non-significant difference between the groups, you could do it again, and ANOVA won't give you a different answer, right? It'll be the same thing. But the difference is that in ANOVA, you might be able to put more variables in there that might explain the variance, so either on their own or in interaction with the group. So group on its own might not explain it, but group with age, for example, there might be a developmental difference in how the groups go across something. So ANOVA lets you add in more predictors that will try to explain the variance. T-test is just the one group. Good? Okay. So let's look at the different sources of variability, right? This is just another way of looking at it. I think it's worth spending some time on this, but so let's say we have our population that we're estimating, which is this orange group, okay? And within our global population, we have a group, the blue group, and we had the group that got the treatment. And we asked them, these are their different scores on our measure of happiness. So you'll see Y11, the first is I. So it's basically this Yij. You've probably seen this in equations before and been like, what is this? So I just means the person and J is the group that they're in. So Yij is the ith person of the jth group. Okay? So each person is their own individual and they are within a group. And we're going to use that in order to look at the sources of variability. Okay? It's just kind of annotation. So we can partition the total variability, the orange square, into the variability between the groups. So that's J versus J, right? Blue versus green. And the variability within groups. So that's from subject to subject within the blue group, I versus I. The difference between two groups, we call this a factor or an independent variable or predictor, right? So we're trying to predict, based on this variability between groups variable, the variance in our orange box. So in our case here, we have the two possible values, pill versus no pill, right? We have two groups, no pill, pill. That is two levels of this factor. This is terminology, but it will be important when we talk about what things we're moving into our ANOVA. Okay? So ANOVA, it's typical to call it a factor instead of an independent variable. And how many levels is how many subgroups you have, how many subdivisions of that variable do you have. Okay? So bear with me, one more slide on this. Quantifying this variability, each person has a deviation from their grand mean, the orange, that can be split into the between groups. That's the deviation between the group means from the population mean. So that's blue group compared to orange group, and then green group compared to orange group. And then each subject also has a within group, right? So they have a deviation of individual people from their group mean. So that's kissy face versus blue, for example. Okay, and then I'm putting this up here because I learned to do ANOVAs by hand, which sounds really daunting, but has really given me a good understanding of ANOVA. And so I'm going to put up the terminology, and then you'll see when we get to the SPSS where all of these numbers come from. Okay, so A, what I call the factor between groups, that's blue versus green, and then subjects within group is S, subjects within A, S bar, like /A. Okay? Now the deviation of the variance, like we had looked at with the cones and the deviation from the mean, we talked about this before. We were going to square the deviance from the mean and sum them up, and that is called a sum of squares. Have people seen this on their outputs in SPSS, sum of squares? So you sum up the different squared variances of each person from their mean, but also of each group from the population, right? And so the total variance in your model, because remember we're trying to partition the variance, the total variance is the sum of squares of each individual, the groups up here. So for example, group blue versus the total group orange, plus the variance that is in each person within their own group. That's the whole variance that we have to explain, right? We get to explain it in different ways. We're going to divide it by the number of observations minus 1. I don't know why minus 1, but that's the degrees of freedom. And so the SS, sum of squares divided by the degrees of freedom, gives us the mean squares. So everybody's seen that in their output. MS. Again, the mean squares total is divided into the mean squares that is represented by the variability between groups and the variability of each individual within its group. That gives us an F value. So if you divide, again, if you go back to that earlier screen, the variability that is between the groups over the variability of each person within its groups, aka error, you get an F test. And so this F test represents the extent to which the between group variability is bigger than the within group variability, right? We were looking at error over error and then error plus treatment versus error. How bigger is that difference between the treatment groups compared to the error within the groups? And so you actually, we're not going to do this step, but you compare this F value to a F table. There's a critical value you compare it to, and you determine whether it's significant or not. So is this value, this magnitude of the difference between these two sources of variability, is it greater than just chance or not? Okay, I know that was a lot of theory. It might make more sense when we do this in SPSS, but is everybody kind of with me so far? Okay, basically what we need to know is we're partitioning the variance in our DV into different sources of variability. One source might be the group differences, one source might be error or the variability between groups. Within groups, I mean. Okay. Congrats on making it through that. Let's get to SPSS example. Okay, so to begin, we're going to do exactly what we did before. We're going to look at group differences in the voice performance. Okay, this is very similar to what we did in the t-test, right? So we're going to analyze, come on, over here. Yep, analyze. Now we're into general linear model, and we're going to choose univariate. Univariate is if you have one dependent variable. Multivariate is two or more, and repeated measures is something else that we'll get to. I won't explain right away. We're going to do all three, okay? Probably not today, but in this workshop. Okay, so here's our little window for univariate. Here's our dependent variable. So if I asked you guys, I'm going to look at group differences, so my group being epilepsy versus control, and I want to know the group differences in voice accuracy. What do I put in my dependent variable? Just shout it out.
Voice accuracy.
Yeah. And remember how I called our group differences factors? Here they go, right? Fixed factor, random factor. Fixed factor, we're not going to spend a ton of time on this. Fixed factor is if you know all the possible levels of this variable that you're interested in. Random factors if you have only measured a subset of the relevant levels of that factor in the world. Most of the time, we're going to use fixed. So for this example, I have controls versus epilepsy. That's good enough for me. My theory doesn't say that there's other types of things that I should be measuring, and I'm not. It's a little bit of a conceptual difference, but most of the time, if you put in as a fixed factor, you're probably going to be fine. Okay? So over here, this is changed by the different versions of SPSS. It looks a little bit different in different versions. Like this is not what I have on my computer, but under options, you can ask it to print out descriptive statistics, estimates of effect size. So that is another way of saying my factor I just put in there, how much of the variance is it explaining? Okay, so you've heard of effect size being more important than p-values now, like how it might be statistically significant, but is it really meaningful? This is where you would get that info. And parameter estimates are really if you have a continuous variable, which we'll get to a little bit later. As a habit, I always click these three. Click continue. Estimated marginal mean. So in old versions of SPSS, in options, if you have an older version on your computer like I do, this will be part of the options window. Okay, but basically you're asking it to give you the estimates for each of the means for each of my groups. Okay, so here I moved in overall, so that's overall the voice average performance, give me a mean for that, and then give me a mean split by each group. And compare them. Okay, this is in your slide so far. I'm going to click OK. Okay, so down up at the top, we get a little bit of a recap of the stuff that we put in. So we put in group as a factor, control versus epilepsy. Here's how many people we have in each group. Here's our dependent variable, and then it gave us descriptives, the mean for control, the mean for epilepsy, and the mean overall. These are all values that we saw earlier today. All right. Tests of between subject effects. Between subjects, that's A, factor A, between groups. Within subject effects is something a little bit different that we'll get to when we talk about repeated measures, but for now you're looking at the effects that are between subjects. What does between subject mean? It means that each person has one value of that variable. You can either be a control or an epilepsy patient, right? You can't be both in this model. We'll come back to that when we do with repeated measures, yeah.
So then within subjects is when it's like the same person, but like at 2 different times?
Yes, exactly, yeah. So here we're interested in group. Okay, over here, look at it, check this out. Sum of squares, degrees of freedom, mean square, F statistic significance. Okay, these are all the things I put up in those equations earlier. A partial eta squared kind of gives us our effect size, but here we see that there is a significant effect of group on voice average. This is very similar to saying there is a significant group difference on the voice average that we did in a t-test. So when some of you are asking, is it different? No, it's going to give you the same result because we've only asked it one variable so far. Now, ANOVA gives us more flexibility. We can add more variables, like we'll do in a second. But as far as we've done so far, this is not different from a t-test. We've asked, does group explain the difference between two groups? Is there a significant difference between the two groups? So far, we've done the same thing, just conceptually a little bit different way of explaining it. Okay, so here is our error. So that was the A, and this was the subjects within A. So technically, mean squares up here, this is the effect of treatment plus error, and this is the effect of error in our example. This would be cool if I could get someone to do it on their calculator. Can someone verify that this divided by this is equal to approximately this? Who has a calculator on their phone real quick?
We just multiply by 100.
Yeah? Yeah, so you can already see, right? It's 11, essentially. So if you do mean squares of your group over the mean squares of your error, you should get something approximately like this. Yep? Cool? And it's significant, okay? So we're going to skip this because I'm going to come back to this in a second. Now, if I scroll down to estimated marginal means in my output, I have my grand mean, which is, okay, I'm not splitting anybody, my whole group, what was their outcome, which is the performance, right? But then here I asked it to give me estimates by the groups. So then I can see, again, like in my descriptives earlier, I can see, you know, okay, this is the direction of the difference. An F-test only gives you the fact that there's a difference. It does not tell you where it is different across the groups. Okay, if you have more than two groups, you have to do pairwise comparisons down here. So when I asked it, I clicked on the box that said compare means, that's what this is doing. So in this case, it's kind of redundant and silly because there's only two levels to my factor. So of course, if there's a difference, it's going to be between the two levels. But if I had 3 levels, say I had controls, epilepsy, and a TBI group, right? Then I could look at the pairwise comparison. If I found a main affected group, what that would tell me is that somewhere in my groups there is a significant difference. But then I would have to look at the pairwise comparisons to see which pair is significantly different. Because it could be that the controls versus epilepsy are different, but then epilepsy versus TBI are not. Okay? So that's only really useful if you have more than 2 groups. And that's just a repeat of this up here. Any questions about this? Are we good?
So you're saying so far what you did isn't really different than what you could do with the t-test.
Exactly. So let's take it a step further now. I've been teasing about this. Here we go. Let's go back to our univariate, but this time I want to know, does gender play a role? Right? There's some evidence out there that female participants are better at emotion recognition tasks than males are. Let's see if that makes a difference, okay? So I'm going to throw it into my fixed factor. Fixed again because I have measured male and female, and in my particular design, I'm happy with calling that the only 2 factors I'm interested in. Could be different depending on your group, right? Your experimental design. Okay, so I'm going to move that over. Now back in my estimated marginal means, I'm going to want to know, okay, give me the, okay, overall disappeared for some reason. Give me the group, it's already there, gender, and then also the interaction between the two. So split it up kind of like a crosstab. Give me for each group and gender, so female control, female epilepsy, male control, male epilepsy. Give me their estimated means on the task, performance on the task.
I have a
continue.
quick question.
Yeah.
Sorry to interrupt you.
Yeah.
So your group here is, so you have two categorical groups.
Mm-hmm.
What if you had a continuous, does it matter?
Yes, it does matter. Can I put a pin in it? Because I will add that in.
Of course.
Yeah. So yes, but thank you for pointing it out. So far, it's only categorical variables, right? You cannot put a continuous variable in this so far. You can, and we will. But so far, if you're putting something in a fixed factor or a random factor, it has to be categorical. Okay, so far. Okay. Make sure I got everything. All right, here we go. So here's our new analysis of variance. Here it gave us the between subject factors that we put in. Here's the labels that we've assigned to them, the descriptive statistics by each group. Now this should be a little bit familiar. So we have our effective group, sum of squares, mean squares, F-value, significance. We have our main effective gender, and the interaction between group and gender. Okay, so we can look at our significance here. Which one is significant?
Group.
Yeah, group is the only one that has a p-value that's less than 0.05, right? 0.05, I should say. So what this is telling us is that there is an effective group on voice average performance, there is no effective gender, and there is no interaction. An interaction, this is how you interpret it. You can interpret it one of two ways. The effective group depends on which gender you are, or vice versa. The effective gender depends on which group you are in. In this case, it does not, because it's not significant, but that is how you interpret an interaction. So the effective one variable on the other depends on which group you're on in the second variable. What this also means, this is important, this means that the effective group on performance exists above and beyond the effective gender. So we are, in effect, controlling for gender by putting into our model. Okay? So the main effective gender is not significant, but your main effective group is significant even when controlling for gender. Good? Okay. Let's look at the variables down here. So we looked at this earlier. Here's our pairwise comparison. Now we have a new section for gender. It gave us the means, and you'll see females had 36% and males had 32%, but it is not a significant difference. It's not a meaningful difference, meaning that there was more variability within each person and their gender group than there was between the gender groups. If you go back to our little equation, this is what a null effect means, that the error, quote unquote, within groups is bigger than the difference between groups. Therefore, there is no difference between the groups. Good? And we've got down here, we have our group by gender. Okay, this will be the last thing I show you for today, but let's go ahead and plot what this means. Okay, let's pretend that there was a significant difference for fun. I just copied this, and I'm going to open Excel, because this is how I do it. I don't really waste time trying to figure out an SPSS. I don't like the SPSS graph stuff, so I copy the variables here, and I can plot this, right? So you have to change a tiny bit the way they're set up, because you have to kind of create a 2x2. Okay, so I've just kind of repositioned the variables here. Select them, insert, let's do a bar graph. So this is what it looks like. Okay, so let's pretend that this was a significant thing, then we would be looking at this, right? So here are the values that we plotted. We're seeing that in both groups, essentially, the females are more accurate than the males. Okay, so this is to kind of visualize an interaction going on. Now you don't know really if this is different from this, if this is different from this. I mean, this doesn't look different from this, but like, how would you know, right? A couple things to help are that you could plot the standard errors, right? Error bars, more error bar options. You could plot them for each group. These are all in your slides, so I'm not going to spend too much time on this, but which is basically, if you have any questions about doing this, you can come see me, but I put a little note. So you could plot, and I'm not going to do it for the other group, but you could plot to see this is the estimate of the variability, right? So if your bars overlap, it's not likely to be significant. But to test this formally, you have to do the following. You have to do what's called a simple effects test. So go back to SPSS, go back to your univariate. This time, paste the syntax. There is no way to do this without the syntax. There's no way in the click-through to do this. Okay? So here you'll notice that I have a compare little line that was added for group and for gender. Right? I don't know why that's twice, but so what that did is it gave me those pairwise comparisons I was talking about, the two pairs, and looking at it, it gave it for me for each of my main effects, right, my two genders, but it did not give it my two groups, but it did not give it for me for the interaction. So here I'm going to add it myself and say compare group. This, by the way, adjustment is least significant difference. In the drop-down menu, I put this on your slides. You can select Bonferroni or what did I do? That's not good. You can select Bonferroni or SIDAC or other adjustments to your pairwise comparison if you have multiple comparisons that you're making and you're having to adjust for that. And then I'm going to copy that and then just say gender here. Okay? I'm going to select all of it. I'm going to run it again. So the difference will just be that down here I have a group by gender and then group by gender again. So I have these values that I just plotted in Excel, but I also have this extra little pairwise comparison table underneath it. So under the first one, I have it by female, and then within the female group, comparing controls versus epilepsy. And then within the male group, controls versus epilepsy. And then because I asked for the flip side of it, now I have it the other way. I have within control group, are females and males different? Within the epilepsy group, are female and male different? So you can see here that no, there's no significant. I mean, this is not a significant interaction, so it's kind of silly that we're doing this, but over here you can see that there is a significant difference here. It's less than 0.05 female control versus epilepsy. So if I go back to my Excel, in my female group on this side, this is significantly different from this. But the other bars are not significantly different. So this might be interesting when you're trying to understand where is there a difference in my interaction. I have an interaction somewhere, somehow, the two groups are being different, or the effect of one group is different depending on the effect in what group you're in the second variable. And these simple effects test will tell you where that difference comes from. So if this were significant, we would be saying that the effective group depends on your gender, or effect of your gender depends on group. In this case, our significant pairwise comparison tells us that if you are female, there's a difference between control and epilepsy, but not if you're male. Does this make sense to people?
And is this the same as a moderation model?
Pretty much, yeah. Yes. Yeah, because the moderation model is essentially testing an interaction between your independent variable and your moderating variable. So yeah, it's the same. Okay, we're almost at time, so I'm going to end right here, but the next thing we will do is to add a continuous variable in here and how we're going to do that. Okay, then we'll also do multivariate models and then repeated measures, and then do some sort of recap with a little maybe flow chart I'm working on to decide what test to use when next week. Before we break, is there any questions? All right, thank you, and thanks for your patience again.
I'm not gonna do a flow chart. Those are really good.
Yeah, I'm kind of working on it. Did I? Oh yes, here it
I
is.
have a question. So why